networks. It is normally used as a training algorithm in feed-forward networks, which is carried out in two phases. First is the forward pass or the phase with the forward pass, where we apply the inputs to the input layer, and that is input is propagated from input layer towards the output layer through the hidden layer units, and output is computed. Once we have the output is then compared with the desired or the target output. Error is computed, and in the second phase of the backward pass, this error is traversed from output towards the input layer units so as to adjust the weights such that this error is eventually reduced. So it is based on the gradient descent algorithm, and this is actually used in the feed forward networks with at least one hidden layer unit. Okay, so we can have any number of hidden layers, but at least one hidden layer is required for use of backpropagation. So before we start with the backpropagation, let's have a quick recap of what is the gradient descent. We have already covered gradient descent in the previous lecture, but I'll just take a recap of that. So this is my cost function, which is the error function derived from the mean squared error. Okay, and this is W with respect, that is the weight of the interconnections. Okay, so I have made by error cost function a function of the weights of the interconnections, and I plot this as an error surface with respect to this weights. Okay, so let there be initial point, which can be any random point A or B as shown in this figure. So it can be on the either side. So eventually what is my gradient descent algorithm going to do? My gradient descent algorithm, it is going to change the weights in the direction such that we move towards the point C, which is the minimum energy point or the minimum point for the cost function we are plotted or we are focused. Okay, so this is achieved by finding the differential of this cost function with respect to the parameter, that is weight, and at this minimum point this has to be reduced to 0. So gradient descent, it is used to compute the minimum value of a cost function with respect to a given parameter, and it is carried out till the gradient vanishes, that is till the slope is reduced to 0, and at this point, which is point C in the figure, the differential becomes 0 or too small. So this is how the gradient descent works. So normally the gradient is such that it always leads to increase in the cost of the function, and by algorithm it is going to be in the parameter always change the parameter in the direction opposite to the gradient. So gradient, it increases the cost function, and our adjustment of the parameter, it is opposite to this gradient, that is it is proportional to minus Gn, where Gn is the gradient or the slope. So it is always trying to reduce the value of this cost function we have plotted. Now with this knowledge, let's start with a backpropagation algorithm. So for that, consider a feed-forward multi-layer perceptron network in which we are having 3 layers. Let the structure be L cross M cross N, where L is the number of neurons in the input layer, shown by this blue circles in the figure. Then we have the M neurons in the hidden layer, okay, shown by these yellow circles in the figure. And we have finally the output layer, which is shown in the green circles, having n neurons in the output layer. So I have the inputs which are applied to my input layer units, and the input from this uh, from this input layer units is passed as the input to the hidden layer units, and the output of these hidden layer units is passed as the input to the output layer units, and finally we get our outputs which is computed. So the subscripts I, H and O, they denote the input, hidden and the output neurons. Then we have the weight matrices, the matrix V that denotes the weights on the connections between the input and the hidden layer units. So it is a matrix of L cross M, and we have the associated weights here shown by the matrix V. Then we have that matrix W, which shows the weight on the interconnections between the hidden layer units and the output layer units, and it is of the order M cross N, where M is the number of neurons in the hidden layer and N is the number of neurons in the output layer. So I have four matrices involved. I is the matrix of input, V is the matrix of the weights between the input and the hidden layer unit, W is the matrix of weights between the hidden layer and the output layer units, and finally we have a matrix O, which is the matrix of the outputs which have been computed. Okay, so with this knowledge we start with the backpropagation algorithm. So the first step to the backpropagation algorithm is, okay, we should have the target values also available for all the n neurons in the output layer. So with this knowledge we start with the backpropagation. So the first step is to compute the input. So for the input layer computation, my input units, they are simply the units which are passing on receiving the inputs and passing those inputs to my hidden layer. So there is no computation as such. The output of these input layer unit is same as the input which is applied. So for all the n neurons in the input layer, I can simply compute by OI, that is the output of the input layer, as simply equal to the inputs which are applied to these input units. So L input units are there in the input layer. Once I have my OI available, now this OI, which is the output of the input layer, this is given as input to my hidden layer units. So I consider the sigmoidal function as the activation function for my hidden layer units. So for any pth unit, any pth neuron in the hidden layer, the input which it receives is nothing but the weighted sum of all the inputs coming from the L input layer units towards this neuron P in the hidden layer. So this gives me the input, summed input received at this pth unit in the hidden layer, input which is coming to this pth unit of the hidden layer. So P indicates the unit which is there in the hidden layer and H indicates the hidden layer unit. Okay, so I get it by computing the weight of the interconnection which is coming from the first unit in the input layer and the input which is coming from that unit. Okay, that is OI1. Okay, so similarly the weighted sum is all the L inputs in the input layer, they are giving input to this pth unit in the hidden layer, and each of this is associated with the weight which is given by V. Okay, so I compute this as a weighted sum. So this IHP is giving me the input I am receiving for any unit in the hidden layer. So once I am able to calculate it, I will apply the sigmoidal activation function to this weighted sum with my theta considered to be as 0. Okay, so I simply apply the definition of my sigmoidal unit, that is nothing but 1 over 1 plus e raised to power minus x. So x is nothing but the weighted sum. So theta in this case is 0 and this x is the weighted sum, which is what we are getting from here. So once we have computed IHP, I put the value as IHP in this, and what I get is the output of the pth unit in the hidden layer given by O for output, H for hidden, and P for the pth unit in the hidden layer. So with this value, I now go to the next layer. That is, so I already have my output computed for the hidden layer. So this output from the hidden layer, it is going as an input to the output layer unit. So for all the m units at the hidden layer, the output will be computed, which forms a matrix as OH. Okay, so this is for the mth unit, this is for the second unit, this is for the first unit, and so on. Mind it, in this we are eventually taking my theta to be 0. We can take any value, but for our current example we are taking it to be 0. So once we have this matrix available, now I will calculate the input which is going to the summed input which is going to any qth neuron in the output layer. So any qth neuron in the output layer will receive inputs from how many units? From the m units in the hidden layer. Okay, so that is computed as IOQ. O stands for the output, I stands for the input which is received by the output unit. Which unit? Qth unit. So that is just generalizing. So that is what, how do I get? I get it by multiplying this matrix with the weight matrix W, which is there between the hidden layer units and the output layer units. So for any qth neuron, it is going to receive inputs from the all m units of the hidden layer, and each unit is attached to my this qth neuron by a weighted connection. So that weighted connection is given by this component of the weight matrix W multiplied by the output of the each hidden layer unit, which is being served as the input to the output layer unit. So with this knowledge, I am able to compute what is the input which is coming to my output layer unit. Once I know what is the input I am going to get, I am again going to calculate what is the output of my any output layer unit assuming a sigmoidal activation function. So it is again calculated as O for output, the second O for again the output layer unit, and which unit? Qth unit. So that is simply applying the definition of sigmoidal unit. So value of x here is nothing but the weighted sum of all the inputs which have been received on the qth unit of the output layer. So with this I am able to get, so for all the n units in the output, I will get a matrix O which is of the order n cross 1. Okay, and why n? Because n output units are there in the output layer. Okay, so once I have this, I now consider my target or the expected values of the outputs for all the n units in the output layer. Now I compute the error. Again, error would be computed for all the units individually in the output layer. So for the qth unit, my output is taken as a mean squared error, which is given by this. So using the gradient descent method to minimize this error, I calculate this and then I have to backpropagate. Okay. So for all the nth patterns, this is going to be averaged over all the values of n, some values of n. So for n patterns, this would be given by 1 over n, and the summed error of mean squared error of all the nth patterns applied. So to understand this, let's see what we are now going to do. So this is what this green neuron is representing my neuron in the output layer. Let it be the jth unit. So whatever is the input coming from the hidden layer units, and each of this associated with the weight, my weighted sum is given by this Vj. L is for the lth pattern which has been applied. Okay, so I calculated it as the weighted sum. So this is my activation function. So this psi is going to give me my activation function. Phi is going to give my activation function, which is nothing but sigmoidal function. So let the output after application of the sigmoidal function be given by yj for the jth unit for application of lth input pattern on my network. Okay. So with this, I use the gradient descent. The weight change, it is going to be proportional to the gradient of the error cost function with respect to the weight of the jth neuron. Okay. So applying the chain rule, I can break this gradient into a set of gradients, partial derivative gradients. As first I'll put the total error with respect to the error component which I have calculated. Then this error with respect to the output with respect to the sum input which it received, and the summed input with respect to the weight on which it depends. So now we can compute the values of this entire term by computing the value of these individual partial derivatives one at a time. So the value of the first partial derivative, which finds the error cost function with respect to the instantaneous error, that can be found from the equation 2. The partial derivative of instantaneous error of the jth neuron can be found with respect to the actual output value, that is yj. The partial derivative of the output value yj can be computed with respect to the some weighted sum of all the inputs coming to the jth neuron, that is vj. And this vj value can be, partial derivative can be computed with respect to the sum of the interconnection, or the weight of the interconnection with respect to the weight of the interconnections coming to the jth neuron in question, on which is concerned, on which is required, on which is focus of the weight update. So from all our previous equations, that is equations 1, 2, 3 and 4, we can find the terms. Let's see what these come out to be, how we can solve these. Now from equation 2, I can compute this first term. What is equation 2? Now equation 2, if you go to the previous slide, it is nothing but that gives you the cost function, inner cost function we have computed from the instantaneous error for the jth neuron, where j it extends from 1 to n, that is number of neurons in the output. So this is the squared error. Okay, so if I find the derivative of en with respect to ej, so I can clearly, it will be 1 by 2 into 2 into ej, so 2 cancels out, so this would actually give me with ej only. So this first partial derivative term is going to give me this error term. Coming to the second partial derivative, that is finding the partial derivative of the instantaneous error with respect to the output of the jth neuron. So I know that the error term, the instantaneous error from the equation 1, it is given out to be the target value of the jth neuron minus the actual value of the jth neuron. So if I put this value of Ej in this partial derivative, obviously Tj is going to be a constant. So this is 0. What I'm left with is partial derivative of yj with respect to yj. So that turns out to be 1. So it gives me the value minus 1. So the second term, it is going to give me the second partial derivative is going to give me the value minus 1. Coming to the third. Now third, it is going to get from the equation 4. The equation 4, what does it say? That by output is nothing but the activation function applied to the weighted sum Vj. So Vj is what? Vj is nothing but it is your weighted sum. So all the inputs which are coming for all I. So I will vary from 1 to n, that is number of units in the hidden line. So using this value of yj in this third partial derivative, what I will get is this. It will simply return me the derivative of the function. Okay, vj. And if I put the value of vj here, okay, for one ith pattern, so with respect to this weight wij, so it will return me what? Y. So this input I am the input of from the hidden layer unit I am going to get from this fourth term. Okay. So I am able to solve the value of this gradient of the error surface with respect to the weight parameter as this. Now putting the proportionality factor. So this is my error term. So this is my input from the hidden layer neuron. Now using this equation, okay, of the gradient descent, the change in the weight, it is proportional. So proportionality factor has been replaced by minus eta. So eta is nothing but learning rate. So it is the measure of the step size, that how we are moving, how fast or how slow we are moving on the error surface. That is when we are moving from one point to another along the error surface. What is the step size? That is measured by this learning rate, and it is opposite to the gradient, so there is a negative sign. So I use this equation and I replace the value of this partial derivative by what we have computed here, and what we get is eta into ej, that is error, into the derivative of the output function into input. Now this term together, that is the error term and this activation derivative, this is constituting the local gradient of the error surface with respect to your uh, weight. So this is my local gradient. So with this I can say that change in the weight of the jth neuron in the output is proportional to the local gradient of the output error surface into input. So eta is the learning rate, this is my local gradient, and this is my input which is coming from the hidden layer to the output layer unit. So I can say that change in weight is equal to learning rate eta into the gradient into the input which is applied to the jth unit. So this is what we get as the output of backpropagation, that is how the weights they are changing in case of the output connections between the output and the hidden layer units. We extend this backpropagation of the error to the hidden layer units towards the input layer. Okay, so that the weights between the hidden and the input layer they are adjusted. Okay, so we are extending the same principle for updation of the weight matrix V. So for that again we consider the same error surface. So error surface it is going to remain the same, but now we are going to differentiate with respect to the weight between the hidden and the input layer unit. So I denoted by a curly V, that is weight on one interconnection. It is denoted by a curly V. I've taken a slightly different notation of V here. Now again I apply the principle of the chain rule to this. So applying the chain rule, this is a bit longer chain. Now in this we easily recognize the first two terms, that is the breakup of the cost function and a cost function in the terms of or with respect to the instantaneous error. Instantaneous error with respect to the output of the jth output unit. Output of the jth output unit with respect to the input it is receiving from the hidden layer unit. Now whatever input is there which is being coming from the input layer unit, that is differentiated with respect to the output of the kth hidden layer unit. So be very clear here. I stands for the unit denoting from the input layer. K stands for the unit from the kth layer, and J in this equation denotes the unit in the output layer. So whatever is the output of the hidden layer unit, that is differentiated with respect to the input which is coming to it from the input layer, that is input which is coming to the hidden layer unit, and this hidden layer unit input with respect to the weight matrix which is connecting the input and the hidden layer unit. Okay. So if we go on solving the individual partial derivatives, we can easily recognize the first partial derivative to be equal to the error term as we just solved in the last slide. Next term it is equal to -1 using the same logic we used in the last slide. Now coming to this section. And this is a long set of chain rules. Now this we together denote as a term delta dash k. So I denote this term delta dash k. Okay, and this last term it is going to be solved to the input which is coming from the hidden layer or from the input layer unit. I input, the I it is achieved from this term. How? Because the input which is coming to the hidden layer unit, that is nothing but it is again going to be what? The input, that is the, now this is denoting the summed input. Input which is coming into the weights for all I extending from, so I in this case it is going to extend from I to L, where L is the number of neurons in the input layer. Okay, so if I take the partial derivative of this with respect to this Vik, what I am left with is input only. Now coming to this, now in this case again the error and this term, this is going to constitute the local gradient. So I can very well say that change in the weight of the kth neuron in the hidden layer is proportional to the local gradient, that is delta k, for the nth pattern applied into the input, that is I. Okay, we can easily solve this term, that is delta dash k, as nothing but activation of the activation as the derivative of the activation applied at the kth hidden layer neuron. So that can be easily solved by solving these into virtual terms. So we'll do that when we do the example, because it will make the things little easier rather than assuming what the derivative it is going to be. So that is for the time being deferred to be checked in the example, otherwise it can be easily proved. So for the time being we assume that this whole term, it is nothing but it is the partial derivative, or it is the derivative of the activation function of the kth hidden layer unit, and this along with the error term that constitutes the local gradient of the hidden layer kth unit. And using these values we can actually find the weight of the kth neuron in the hidden layer as proportional to local gradient of the hidden layer error surface into the input which is coming. Okay, so this is how the whole backpropagation it is working. So just summarizing it and seeing what is the net output. So in the backpropagation, first we consider a network, feed-forward network with at least one hidden layer. We make use of the sigmoidal activation functions, both for the hidden as well as the output layer units. Then we calculate the outputs for all the hidden layer and the output layer units. Once we are getting the outputs, I am getting the output matrix O, and I have the matrix T of the desired outputs. I can compute the error for each unit in the output layer. After the error is computed, I can find the value of the average error surface or the cost function, which is derived from the mean squared error. Okay, this mean squared error is then propagated from the output towards the hidden layer, and then from hidden towards the input layer, and in this process the weights are adjusted accordingly so as to reduce or minimize this error. So change in the weights on the interconnections between the output and the hidden layer, they change as learning rate into OH into delta J. So delta stands for local gradient and J stands for the jth neuron, whose weights have to be, whose interconnection weights rather, they have to be updated, and J belongs to the set of all the neurons in the output layer, that is n neurons in the output layer. Now what is this OH? To find the value of this OH is what? Input. OH is what? The output of the hidden layer. So whatever is the output of hidden layer, so whatever I get as the output of the hidden layer, that is going to serve as what? Input for my output layer unit. So that is same. So it is nothing but it is same what we had initially denoted by yi. For the weight updation, wij, where I was the input or the hidden layer neuron and j was the output neuron. So to update this weight, I was considering the output of the hidden layer ith unit, which was coming as the input to the jth output unit. Are we getting? So whatever is my, this is my hidden layer and this is my output layer. So I have number of neurons. So this is my output layer to explain. And so whatever, so I is going to vary for the hidden layer. So whatever is the output I have calculated here, that is going to the serve as the input here. So whatever is the output of this hidden, so H stands for hidden, that is going to serve as the input for the output unit O. So H stands for hidden and O stands for. So I hope it is very clear to you what does this imply. So we have simply replaced yi by OH, that is the output of the hidden layer or input of the output unit. Either ways you can say. Similarly, for the weight matrix between the hidden and the input layer units, delta V, that is change in the weight share, it depends upon the learning rate, the input which is coming I from the input unit, and the delta J, which is again the local gradient of the hidden layer unit, where J belongs to M, set of M neurons, where M is the number of neurons in the hidden layer. So I think we are very clear with this. So this is how backpropagation works. So to pictorially represent it, I can just show you this diagram. So in the backpropagation, we first apply the training data. On the application of this training data using the weights on these interconnections, so this here it will be V and here it will be W. So weights V and here we have the weight matrix W between the hidden and the output elements. So first, using these initial weight values, which are the random values, we compute the outputs of the hidden layer. These outputs serve as the inputs to the output neuron, and then we finally get the output here, which is nothing but yj. Once I have yj, I can compute the error. This error is nothing but target value minus the actual value. Once we have this, we can compute our error cost function, which is nothing but mean squared error. Now this error, it is actually back propagated from output towards this hidden and from hidden towards these input units, so as my weights V and W are adjusted so as to minimize the error in the next epoch. So this is known as my training phase. Once my training is over, it means my learning, backpropagation learning of my network is over. So once it has learned, then my weights are going to get fixed. So now my weights V and W, they will be fixed. I will apply any test data on the inputs, and corresponding to that I should get an output which should be an optimal or a reasonably close value to my actual or the desired output. So this is the prediction phase once the learning is over. So I think we are clear with backpropagation algorithm. Now we'll actually take an example to solve a small network problem and update the weights using the actual functions, output functions, actual structure of a network, and see how the backpropagation works. This we will do in the next class. Thank you so much.